Now let's have a look at some of the frequencies for M.A.R.S. Here's a large frequency chart which is shows basically a variety of different frequencies, and effectively M.A.R.S. frequencies go all the way from medium frequency through all of HF, that is all the way from 2 megahertz all the way up to 30 megahertz. And let's look at just the HF spectrum from this chart, which is the third row that's highlighted here. If we look at that third row in a little bit more detail, we can see that there's a lot of different frequencies involved, and the M.A.R.S. frequencies, which are fixed singled out frequencies, they're basically in the red coloured areas in this particular chart, and they're always outside the amateur frequencies, which are shown in green. You can see the largest green segment there is in the upper part of that chart, from 3.5 to 4 megahertz. That's the amateur 80 meter band. Now all M.A.R.S. frequencies are outside amateur frequencies, and sometimes they're close enough to easily convert equipment such as linear amplifiers with little or no modification. Sometimes it's a little bit more involved. So let's have a look at what can be involved in terms of converting some equipment. If we look at M.A.R.S. frequencies being outside the bands, how can we actually do things? Well, how do you transmit on a regular ham receiver? Well, if you've got a general coverage synthesized receive capability, then yes, these can usually be modified for transmission. The methods used to convert a general coverage receive capability transceiver is to remove certain diodes, alternatively remove certain wire links, or remove solder bridges. Sometimes it can even be done purely under software control. So there are a variety of ways for quickly converting a standard transceiver for M.A.R.S. usage. Now let's have a look at what antennas are available for M.A.R.S. M.A.R.S. has a variety of different nets. It has both regional nets and transcontinental nets. Now different antennas are clearly required for different types of net, and difficulties can occur because of beam pattern, the azimuth plus elevation response. Do you want an antenna to work on a single frequency or multiple frequencies? The antenna impedance, if you're going to use it across multiple different frequencies, is going to vary widely. You're certainly not going to be able to have multiple different antennas unless you've got enough space for an antenna farm. So to have an individually tuned antenna for each and every M.A.R.S. frequency that you could be asked to operate on is like having every single possibility of antenna for the entire shortwave spectrum. Clearly not a viable proposition. Now different antennas have different characteristics, for example loops, dipoles, extended double ZEPs. They all have unique characteristics, and what you need to do is to use the right one for what's needed to be achieved. Now to help you decide that, what I'd like to look at is the concept of antenna resonance with height. What this slide shows is how an antenna needs very little trimming for a height of half a wavelength. But as the height is reduced, the antenna length needs to be trimmed progressively more in order to maintain resonance. So what we've effectively got here is an effective length of the antenna is half a wavelength, but the actual resonant length has to be trimmed a little bit more. You can see at half wavelength height we've got a resonant length of 0.49 wavelengths. So that represents a reduction of 1% per leg. And if you look on the right hand side of column there, the impedance at resonance, you can see that what I've given is what the impedance would be if we didn't trim the antenna. In other words, if we had the antenna exactly half a wavelength long and simply looked at what would its impedance be as we change the height, we can see that it rapidly becomes non-resonant. In order to achieve resonance, we have to trim the antenna successively more as we lower it in height. Now let's have a look at some antenna patterns as this height varies from half a wavelength down to 3/8 of a wavelength, down to 1/4 of a wavelength, down to 1/8 of a wavelength. Here we can see a set of antenna patterns, and again this is looking at that same half wavelength long dipole, center-fed dipole. And we can see that when it's elevated to a height of half a wavelength, you've got quite a nice antenna pattern. This is the top left one with a 7.7 dBs relative to isotropic. As you lower the antenna down, the overall strength starts to reduce, and the pattern gradually becomes more round and more spherical in shape, until in the end, once we get down to the bottom right is 1/8 of a wavelength, where height is 0.125 wavelengths, so that's 1/8 of a wavelength. You can see that the peak of the pattern is vertically straight up, and that is actually represented as 5.7 dBs relative to isotropic. Now clearly that pattern is quite good for different types of communication where you've got near vertical incidence skywave. Let's have a look at those patterns again more in a 3D view, because I think that will give you a little bit more information as to how they look. Now if we look at the top left, you can see how the pattern is fairly squashed. This is basically half a wavelength high and is quite a good indication of what is happening. The beam pattern is basically broadside to the antenna, so the beam is going basically along the x-axis there, and you can see this got a very much a solid shape of a primary direction. There's very little radiation going upwards. Now as we lower that same antenna and reduce it in height to the top right there, you can see it's reduced in height to 3/8 of a wavelength. You can see that it's becoming more of a ball shape, and as we reduce it even further to 1/4 of a wavelength at the bottom left, it's becoming even more of a ball shape, and as we reduce it even further to 1/8 of a wavelength, the antenna changes, the antenna pattern changes quite considerably, so that most of the radiation is straight up, which is really good for near vertical incidence skywave. You'll also notice that in that bottom right case at 1/8 of a wavelength, that the pattern depends less on the orientation of the dipole as it is lowered. So as a result of becoming more ball-like, you've got a more omnidirectional pattern that is independent of antenna orientation. Now let's have a look at feed line and impedance. Now feed line can be a coax, can be ladder line. There's many different types of feed line that can be used. But the important thing to bear in mind with all feed lines is that if the antenna impedance, which I've written here as ZA, is equal to the characteristic impedance of the feed line, Z0, then any length of feed line will actually preserve that value of impedance. Now in most cases you've very rarely got an antenna with a perfect impedance of 50 ohms that directly matches your 50 ohm coax. So as a result, there's always going to be a difference in the antenna impedance and the impedance of the feed line. Whenever there's a difference, you will get a transformation of impedance occurring.